Hi, can you hear me okay?
Yes.
Excellent. I'm using a different microphone than I normally use. Uh, all right, let me get started. Halloween is coming up on Sunday, so I do have a Halloween theme to my presentation, and my Zoom background is the Eastern State Penitentiary in Philadelphia. And this photo was taken when I went to a haunted house there. So if you're in Philly around Halloween, definitely check it out. All right. As Becca mentioned, I will be talking about formulas for technical interview solutions and implementing priority queues with Heaps. I'll start off with a small introduction about myself, and I've decided to swap my topics. Normally I do a non-technical topic and then a technical topic, but we'll start with Heaps and then the formulas for technical interview solutions. After each of these sections, I'll stop for questions, and I'll also keep an eye on chat for questions. Q&A at the end, ask anything about the presentation or really anything you want about interviewing or data structures and algorithms prep. So about me, I am a senior software engineer. I just started at Wayfair last week, so don't ask me about Wayfair, but give me a few months. I've been a software developer for 10 years, primarily Java, backend, cloud, AWS, or GCP. I do have a Twitter and a LinkedIn and a YouTube. The YouTube is mostly practice recordings of these presentations I do for Women Who Code Philly. If you do want to message me on LinkedIn, please send a message where you found out about me. Otherwise, I get a lot of spam. All right. Starting off with implementing priority queues with Heaps. So what is a priority queue? If you're familiar with data structures and algorithms prep, you've looked at stacks and queues, or you'll eventually get there. When you think about a queue, it's a first in, first out sort of list data structure. When you put an item in, the next item you expect to get out is the first item you put in. So first in, first out. When it comes to a priority queue, you put an item in or many items in, and you want to get out the highest priority item. It's no longer first in, first out. A priority queue is an abstract data type. This idea of I put an item into something and I get the top priority item out of that thing is an abstract concept. There's no concrete implementation like it has to be a linked list. So this interface can be implemented in many different ways. Another thing to just point out explicitly, when you do have a priority queue, you need to define a function that compares the priority of each item. Depending on your language, that might be an interface in Java like a comparator, but you do have to say, for my priority queue, I'm going to say that the minimum integer is top priority. And that's the interface I have here. This is written in Kotlin, but hopefully all the code can be understandable even if you don't have a Kotlin background. So I'm going to implement the interface for a minimum integer priority queue. There will be 4 methods: find min, get min, insert, and isEmpty. I'm not going to show the implementation of isEmpty. I'm going to focus on the find min, get min, and insert. If you look back in your minds to regular queues, you have push, pop, and peek. I'm going to go into more detail of what these are, the find min and get min, but find min you can think of as peek, get min as pop, and insert as push, if that's the interface you're familiar with. Now let's get into heaps. You will hear the term heap used in 2 places in computer science. The first one is the data structure, which we're talking about today. And the second one is memory space allocated in RAM. We are not talking about that one today. That is a different topic. Though, of course, if you want to ask me about it at the very end with open Q&A, go ahead, but not for this part of the presentation. A heap is a special case of binary tree. So you're going to recognize what this data structure looks like if you're familiar with binary trees. A heap is used to efficiently manage a collection of prioritized items. And I'll show you a comparison with a list structure instead of a heap structure. When we talk about heaps, we have to have a priority, right? So we're implementing this priority queue. When we talk about heaps in theory, we tend to talk about integers. And to prioritize integers, you have a minimum or a maximum. So we'll talk about a min heap or a max heap. Today, I'll go through the implementation of a min heap. So the minimum number is the top priority item. So when I insert a bunch of numbers, I want to get the minimum. And a max heap is the inverse. So let's look at the heap interface and the priority queue interface. So I've put both max and min here, but use the one that's appropriate for your heap. So find max or find min is get it, but don't remove it. So tell me what's at the top of the queue, but leave it there. Get min or get max is to remove and return the top priority item. So find is like peek and get is like pop. Insert is to add a new item. That one's fairly self-explanatory, or push if you're familiar with that interface. There is a fourth method that comes up with heaps, and that's Heapify. Turn a list or set of items into a heap. I think this is my favorite interface because it's really not a real word. So I get all the squiggly lines whenever I'm doing these presentations. Depending on what you're doing with heaps, there's tons more interface methods. But when we talk about interview prep or understanding the data structure in general, these are the ones that we care about. So going back to the minimum integer priority queue, these are the methods we're going to implement. All right, so this is a tree. It is a binary tree, but it is also a heap. So I'm going to talk about, what is the structure? We're going to go through all the different operations on it and walk through that. What makes a heap different from a binary tree? Because this is a binary tree. We have a root, which is our number 1, which has children 4 and 8. And then we have leaves in the tree, which are 5, 9, 13, and 24. Leaves being nodes that do not have children. A heap is different because it maintains a heap property. The heap property means in a min heap, a node is always less than or equal to its children, or in a max heap, a node is always greater than or equal to its children. So let's look at 1. 1 is less than 4, and 1 is less than 8, which means that it is less than or equal to its children, maintaining the heap property for a min heap. Let's look at 4. 4 is less than 5, 4 is less than 9, so it maintains the min heap property as well. But really keep in mind, this is not a binary search tree and it is not sorted. These numbers do not appear sorted in their level. The only thing you know for sure is that it maintains the heap property. So heaps are trees, and that's pretty clear, but they're also arrays. Heaps are efficient because they are often stored as arrays in memory. Throughout this particular presentation, I'm going to talk about how they are stored in arrays. And this applies to languages where you manage arrays directly. So think C, C++, Java. If you're in a language that you don't directly interact with arrays and you're using lists instead, this still applies, and you may have a simpler implementation. So I'm going with arrays, which are a little more complicated, but the concepts will still apply to lists as well. So how are heaps arrays? Well, you can turn this representation of the heap into an array structure on disk. Starting from the root and going through each level left to right, you store the data in this heap, this tree, into an array. It seems like a sequence of numbers, so how do you deconstruct what's going on here? You have a few simple formulas to calculate the children and the parent of a node. And I'm going to go through some examples of these formulas. So just to introduce this, if a node is at the nth index, so first index, third index, the left child is 2n plus 1, the right child is 2n plus 2, and the parent is n minus 1 over 2. This is extremely useful for any tree question. I cannot stress how this will impact your ability to solve binary tree questions. Consider a question where it says, reverse the order of nodes in a level. Now, that's pretty tricky if you're using reference notation, but let's look at this. 5, 9, 13, and 24 are all right next to each other in this array. So to reverse a level of a binary tree, I just need to swap whatever's between the range of index 3 and index 6. That's way easier than updating all the references to the parents and children. So that's just one example of why this array notation is super helpful to understand, not just for heaps, but for any binary tree question. Okay, so we've got our formula and we've got our heap. So let's do some calculations. I would like to find the left child of 8. So I take 8 is at index 2. 2 times 2 plus 1 is 5. And at index 5, we have 13, which is the left child of 8. Now, what about the right child of 8? We run the formula for the right child, which is 2 times 2 plus 2, just one more, 6. And the right child of 8 is 24. Let's work backwards. What is the parent of 9? 9 is at index 4. 4 minus 1 divided by 2 is 1. And this is integer division, so be very careful here. So we're doing 3 divided by 2. And if you are familiar with math in normal context, you'd say 1.5. But because this is integer division, we drop the decimal. And this is important because you may get some funny answers for your indexes otherwise. And we have at index 1 is 4, which is the parent of 9. So that's how those formulas work. If all you take away from this entire presentation is how to turn a binary tree into an array. Now keep in mind, these are balanced binary trees. So heaps are balanced binary trees, and this works really well for balanced binary trees. That means every level is filled before the next level is filled. This is the most important thing to take away. All right, now let's move on to going through the steps of how these methods work. First off is Feynman, the easiest. Just give me the most important thing and don't change the heap underneath. We found 1. The complexity of this is 1. So we give you 1, takes O of 1. Pretty simple. The good intro here. Now I have this Kotlin code and there's a lot going on here. I'll do a brief summary, but you'll notice the last line is just return the 0th element of the heap. And it's really that easy. If you're storing it as an array or as a list, get 0, that's what you've got. Now, there are other things I'm doing here, and I'll talk about these a little bit later. So I'm initializing memory. So I'm initializing array. And because I'm initializing a block of memory, I do have to separately keep track of what the size of my heap is within that memory. This is what I meant by it gets a little more complicated if you're in a programming language where you're managing your memory yourself. But don't worry about it. Managing the indexes is the same whether or not you have to manage your memory yourself. All right, let's talk about insertion. And I really find heap operations fun. They're one of my favorite data structures, though they do not appear in interviews that much. It's always really great to understand them, especially for trees. I'm just going to keep restating that one. But I do like running these operations. So I'd like to insert a number, and I've got to figure out where to put it. We know with binary trees, or any tree really, that the nodes have these invisible children that don't exist. If you're using a data structure, you're implementing your tree where it has a node and has a left child and a right child. Maybe you use null or none, whichever your language uses to say there's no children here. So we know that there could be children there. And if I have an array, this looks like empty spots in the array. So I've got empty spots at index 7 and index 8. And I know that in my representation of a tree, I've got these potential nodes as well. So when I want to insert a number, I just fill in the first empty spot. So in my diagram, I'm sticking number 2 as the left child of 5, filling in the rows, filling in the levels left to right. And that means I've put it in the first empty spot in the array. But there's a problem. This doesn't meet the heap property. So what do? What we do is we swap them. We swap the child and the parent if the heap property has not been met. So we're going to take 5 and we'll take 2 and we'll swap them. Now remember, because we have that formula, we're at the end of our array, we know where it is, we can find its parent and do a check. All of these operations are constant time. Find my parent, constant time. Swap, constant time. No tree traversal needed. Great. We have another problem where this doesn't meet the heap property either, but we just keep swapping upwards until we meet the heap property. So we take 4 and 2 and we swap again and we're good. We now meet the heap property all the way up to the root. So let's look at the code. The code, it is a bit long, well, long-ish, but it's all the steps that we just talked about. So here, the size of the heap, like I mentioned, I'm tracking the length of memory that's being used by my heap. So if my array size is 5, it has indexes 0 to 4. So I'm putting my new number at index 5 and then incrementing the size by 1. So I put it at the end of the array and say now my heap is +1. Here, this is a special case I'll talk about later, but when you're managing the memory yourself, if you run out of memory, you need to allocate more memory. I'll talk about that later. And if you're using a list structure, you don't have to worry about it. Next, we need to get our current node and our parent node so that we can start comparing. So these are the indexes. So I have where I currently am, what I just added, and what my parent is. Then we do the while loop and swap. So while I'm within the array, so I haven't gone past the root. So my parent is greater than 0. 0 is the root. And if my parent is greater than myself, I need to do a swap. If you've done any in-place sorting algorithms or any sorting algorithms like selection sort, insert sort, quick sort, this is going to be really familiar. You just swap in arrays all the time. Once you finish your swap, you recalculate. You update your parent to your current position because you just swapped them. And then your parent is your next parent upwards. And you keep going until you no longer need to swap or you've hit your root. Okay, so swap and repeat is really the story of heaps, right? And it's going to continue right through to the removal operation as well. So let's talk about time complexity. I talked about how these swaps and these lookups were constant time, but we do have to make multiple swaps. The maximum number of swaps we'd have to make is going all the way from the new leaf to the root. And what is that number? That number is the height of the heap or the height of the binary tree. Now, it's important to note that this is a balanced binary tree. You always fill in a whole node, a whole row before you fill in the next row. And so in that situation, the height of the tree is log n. So in a balanced binary tree, height of the tree is log n. And that's how many swaps we could potentially do. So the complexity is O log of n. And just going to highlight again, it is a balanced binary tree. So don't try to use this height formula for a binary tree where it's just a really left heavy. It won't work out. I talked about running out of space. Arrays are time and space efficient, but you do have to state when you create the array, I would like to have 10 places in memory. And it's going to put that in a memory block. You can't really go over. You can, but you shouldn't. And that is where some security vulnerabilities come in, which is a fun topic, but not for today. They do have a limited fixed space, but they're really efficient because you're just using the same memory block. There's no pointers, there's no extra space to keep track of what's next and what's not. When you do run out of space, you have to reallocate. We have to allocate more memory and then copy it to a new and bigger array. When you do that, you have to say, well, how much bigger do I need to grow it? So this is one of the tricky pieces about using an array-backed heap. It is useful to know about. You can always use a list instead. But this is a concept that is really common to come up if you use a language like Java, C++, C. Just know about it in the interview. You're probably not going to have to go into it in detail. And just be careful. Copying to a bigger array costs O of n time. My insertion is log n time. But if I have to copy to a bigger array every time I insert, now it's O of n. So choosing how to grow it, so maybe double it each time or add 100 each time, is an important factor. But this is where we get into more complexity about how are you choosing your backing data structure. All right, now let's get min. And get min is get the minimum and remove it. Find min is just take a look at it. So we get one, and then we remove it. Done. We do have to fix up what's happening with our heap though, because now our root is missing. So what do? We have an empty spot, so we're just going to put something in there. We'll take 5, which is the last element in the heap, and we will drop it into that empty spot. Now we have a root again, but it doesn't meet the heap property. So what do? We swap, just like we did before. So we look at the parent and the child, and if the parent is bigger than the child, we swap them. Easy. And then we do it again for the next level. So we take 5 and 4, and we swap them again. We go back to maintaining the heap property. So heaps are all about, I hope you like swapping in arrays, just like a lot of the sorting algorithms out there that are in place. Okay, so this code, just if you look at it through a blurry lens, looks very similar shape-wise to the previous code. And I'll go into this one a little bit more in detail. But generally, we move that last element to the root, and then we swap and repeat. So this is the high level part of it. So let's look at that, this code, which is kind of looks like every line looks the same. You just rearrange the characters. Let's go through that line by line. So move the last element to the root. So if the array is size 10, it's 0 base. So take index 9 and put it at 0. So prior to this step, just to highlight, we took that 0th value. So I got my minimum, I stored it somewhere. Now it's okay to overwrite it. Then I overwrite it with the last element. The next line is to empty out the last element. Now, if you're using a list structure, you can just remove the last element and insert back at the beginning. If you're using an array, you do kind of want to, you don't have to null it out if you don't want to, but this is an option where you can say, hey, this is empty now. And then you reduce the size of your heap by 1 if you are tracking the size of your heap yourself. So all of this complexity is just put the last one at the front and be done with it. Next is the swapping. So just like before, we're establishing what we're currently looking at, but instead of going to the parent, we're now going to the left child. So you set the root node in the left child, and then we go back to swapping. If the current one is greater than its left child, then we do the swap and we recalculate current and left child. So we move down. Now, this first check here, just like before, is I need to make sure I'm still within the bounds of the heap. So you can keep calculating indexes, but 1, you don't want index out of bounds, and 2, you don't want to be accessing these pieces of memory that haven't been allocated, or these pieces of memory that aren't in use. Okay. Complexity is exactly the same as before because we're just continually swapping up and down the height of the tree, the heap. So it's still log n. And in this case, you don't need to worry about expanding and contracting so that edge case of running out of space doesn't come up. Okay, so Heapify. I brought this up at the beginning where you can just create a heap out of a collection of items. And while this code is a little Kotlin-y, I say Kotlin-y, maybe not as accessible, the big piece here is given your numbers for each of them, just insert it into the heap. And that's how you can run Heapify. So if somebody says, implement the creation of a heap, all right, give me a set of numbers, and I'm just going to insert them. It's not super complicated, hopefully. Now, the interesting thing about this is the complexity. So you know that your insert is going to be log of n, and you do this n times. So the complexity of creating a heap using Heapify is n times log n, and this will be useful in a slide or two. Now here, as a note on selecting the size of my heap. So I've created a heap class where it takes the size that you want to initialize. This is one option where you can say my heap's going to be size 10. I have 10 numbers. But when you do choose to initialize your heap, you should probably do ×2 or plus 100 or whatever works for you. Because as soon as I do an insert, it's going to do a reallocation. So showing this as seems like a good idea, but it'll be a gotcha because your next insert is going to cost you. Okay, so let's talk about Heap Sort. Heap Sort is an efficient sorting algorithm that's definitely an option if you are trying to remember a sorting algorithm for interview prep. And these are the steps. create a heap with your elements to sort, and then get them in until the heap is empty. There you go. There is your heap sort. So if you know how to use a heap, you can now do heap sort. And the complexity of that is n log n, which is better than n squared. So often in interviews, you're asked to learn an efficient sorting algorithm, and that usually means n log n. So you have things like quicksort, that's really common, or now you have heap sort. I see a question in chat. I will get to that in a second when I have a diagram ready. Okay, so priority queue, I want to implement this. Should I use a list or should I use a heap? Now, when I say using a list, it means you're basically keeping the list sorted. Every time you insert an item, you're going to put it in the correct location in the list. So when I do an insertion, I have to go through each item and say, is this the right place to put this item in my list? And I'll keep the highest priority item at index 0. Now, that means that my list insertion is always going to be O of n. And for my heap, it's going to be log n. With the asterisk that if you're using an array and managing memory yourself, you will have a potential O of n cost once in a while. Okay, so heap looks better. But when you want to get min, you have O of 1. You just get the 0th element. And you update your reference to your list to head. If you're implementing a linked list yourself, you just remove 0, no problem. But the heap is log of n for get min. So maybe it's not as good for this use case. Going through quickly some of the other ones before I address that. Find min is still constant time O of 1. To initialize it, you can do n log n. So we know that Heapify is n log n. To initialize a sorted list, you're probably going to use an efficient sorting algorithm, potentially heap sort, which is going to be n log n. And then when it comes to space, this is where we get into array or not array. Now, an array to store 10 integers is going to take 10 integers worth of space. Efficient, so that's 1n. For a linked list, to store 10 integers, it's going to take 20 memory blocks or 30 memory blocks, depending on how you're doing your references. So it's the integer plus the reference. So it can be more space intensive. Now, does that really matter with some of these examples? Probably not. But if you're talking about something that has millions of items, then this memory comparison might come up. So going back to these operations where the heap doesn't actually look better all the time, the way we talk about this is the average cost of an operation. So if you have 1,000 inserts and 1,000 get min, the complexity is going to tend towards n for a list, even though this one's O of 1 and this is O of n, and it will tend to log n. So on average, over a set of operations, the heap is still going to be better. Okay, so heaps are a data structure and you can use them in algorithms. So what kind of question are you going to get for this? Implement the interface for a priority queue, which is the question we're looking at. Implement a priority queue with better than O of n complexity for all operations. This is one I've seen on some of the coding practice sites. Or just implement a heap. And these are not kind of boring questions, not what you would typically see. So I will say that heaps themselves are not a common interview question. But knowing how to use a heap is going to help you with trees. It'll give you a sorting algorithm, and it'll also help you with arrays and linked lists. So the heap is a sort of collection of a bunch of different data structures, and understanding a heap, implementing it in its operations is going to make you better at all the other types of data structures that it uses. Okay, so there was a question about heaps, and apologies for going back like this. Okay, here we go. So the question is the left node always required to be less than the right node? Now, this is not a binary search tree. There's no sorting amongst the levels at all. The only thing that's true about a heap is that the parent is, or for a min heap, the parent is less than its two children, but the relationship between the two children, there isn't one. except they're both greater than their parent.
Then your get min algorithm will fail.
Sorry?
Then your get min algorithm will fail.
So it doesn't matter which node it swaps with, because you're always going to, oh, I see what you mean. Yes. So you'll do more swaps. Sorry about that. You'll have to do swaps comparing the left and the right child. This presentation was a little faster put together than I wanted to, but that is an excellent point. So let's go back to the get min. So here we would actually want to make sure to check both the left and the right and choose the minimum. So here, when you calculate it, you would choose the minimum between the left and the right, which is a great point. And here you would choose the minimum between the left and the right as well. So thank you for pointing that out. It's been a long month for me.
Glad to be of service.
Yeah, wonderful. Okay, so adventure here. Any other questions on heaps? And now I want to open my IDE and fix that right now, but that's okay. Okay, now we'll move on to part 2, formulas for technical interview solutions. And we've got our scary formula here. Okay, you're asked implement a solution to a problem, and you're thinking, I know exactly how I want to do this. I'm going to use a heap to implement this priority queue, and you just start coding and you think this is going to be great. The problem is that the interviewer doesn't know what you're thinking. The interviewer maybe didn't give you a completely specific description to your problem. And if you get stuck when you're coding and the time runs out, they can't evaluate you on anything if all you have is a half-written solution and you didn't talk about it. So part of answering interview questions is communicating effectively and clearly every step of the way. So here I'm going to give you a formula for your technical solutions. So we're going to talk about implement an interface for a priority queue for the clarifying questions that I'm going to bring up. All right, so first off, you want to restate the question. So many times, even in day-to-day chat without any technical questions involved, you misunderstand people. Maybe you didn't clarify, somebody wanted thing A and you gave them thing B. And the simplest thing to do is restate the question. Is this what you wanted? So I might say, I'm implementing an interface with methods for insert, getmin, and findmin. So the interviewer said, implement a priority queue. And I'm saying, is this what you meant by a priority queue? And if at this point they say, no, that's not what I meant, that's good. It means you're going to go on the right track, implementing the right problem, the right solution rather than the wrong solution. The next one is to ask for an example. All of this is along the lines of, am I actually implementing the right thing? And if you aren't given an example, make one. So if I have a queue that prioritizes lower numbers, then I do an insert of 8, an insert of 4, an insert of 20, and I expect 4. So I don't know if you've encountered these questions, but there are a lot of interview questions on these practice sites where they say, here's a sequence of operations, and this is what you expect back. Not my favorite questions, but questions that are like, given a string, tell me if it's a palindrome. You want to give examples to make sure that you understand. In particular, the palindrome question is always interesting to me because palindrome isn't the most common word, and people who come from different backgrounds may not know what it is. So it's always really important to understand that we're all coming from different backgrounds. So even if it seems obvious to you, you and your interviewer might not be on the same page. So definitely restate, come up with examples. Next, clarify. The previous 2 steps were both under clarification. When we say clarifying questions, though, we typically mean ask about edge cases, things that might change how you solve your problem. Oh, sorry about that. So for example, how are the elements prioritized? What is the maximum number of elements? Are there minimum values for elements? Are there null elements? So different questions like, how should I shape my solution? And this clarification step, you can combine it with the previous 2. You can change the order, but the key is to hit all of them. In some way, get an example, clarify the question, ask for boundaries. Next, once you have all the clarifications you need, or you have a decent sense of the problem you're actually solving, you want to scope it out. When it comes to a priority queue backed by heap, in the example I gave in the previous part of the presentation, I implemented it for integers, but I could implement it for strings or a people object or a library object. So I could implement this priority queue with any data type at all. Am I going to be able to finish that in the 45-minute technical interview? Probably not. So I need to state, I'm just going to implement this for integers, and then I can expand it to generic types. So you want to look at your problem and say, what's the sort of simplest type of solution I can build? So I'm not building an entire application in the interview when that really isn't what they're evaluating. And you do want to state it. Continually talk to the interviewer. Hey, this is what I'm doing. Is that what you're looking for? Because you want to make sure that the interviewer gets what they're looking for, not, let's talk about how to do string comparisons for an hour when they wanted a heap. Next is outline your solution. You know what you're solving, you know what the scope is. So now I want to describe, here's what I'm trying to do. This is your safety net. If you don't have enough time to complete your code, which does happen sometimes, it's not an automatic fail, at least they know where you are going and what you're thinking. So here I say, I'm going to implement this priority queue with a min heap backed by an array in memory. This means I understand the interface I'm implementing. I know about a heap data structure, and I know how to implement a heap data structure. Here they might ask you questions about why a heap, why not a list? And this discussion is part of data structure and algorithm evaluation. This will definitely get check marks on understands data structures and algorithms, even before you've coded. So this is important. Then you want to break it down. So a lot of these steps you're thinking, do I have to do all of these? Sometimes you don't. Sometimes you're asked some very complicated questions like implement a priority queue. By the way, here's 5 methods that you need to do. And you want to break it up into small chunks. So for the priority queue interface, there's methods that you're already given, but there might be other questions where you say, well, here's a chunk about sorting, and here's a chunk to compare strings. If you break it down into methods, you can then focus your answer. There are 4 pieces to my implementation: insertion, removal, expansion, and returning the first element without removing it. And then you can tell them which piece you're planning on implementing. So for example, if I say the first thing I'm going to implement is returning the first element without removing it, does that really tell the interviewer much about your ability to code? Not really. So when you break down your problem, you kind of want to have this large chunk that's really meaningful so that you can abstract away and not spend time on things that are less important to the interview. So think of breaking your solution up into methods instead of one gigantic method. Then you want to start to code. And I'm not going to go into this part. You'll have to practice the coding on your own. Now you've written your code. It's time to walk through an example. And this is a great time to grab the examples that you had before. Here, they will ask you to, well, they don't actually ask you to do this in all interviews, but it's a great idea to walk through your code line by line and say, when you get to this line, you'll see this state of my array. Just like how I had with these examples where each step I showed how the array looked. So that kind of thing, walking through your code. Next, you'll talk about time. Actually, let me go back for a second. You will find bugs here, and that's good. Being able to find bugs in your own code means that you'll write better code and you'll be able to do code reviews as well. So finding bugs, good. Finding bugs in a presenter's presentation so that everyone knows how to implement heaps correctly is also really good. Yes, anyway. So time and space complexity, you'll get to that sometimes. A lot of the times you get to it, sometimes you don't. Sometimes the time and space complexity comes up when you say, I am selecting a heap data structure because it has O log n for all of its operations. So this may come out of order. But generally, you do want to touch on it and say, I'm choosing a heap because it has O log of n complexity. Or I'm choosing a heap backed by an array because it has O of n space complexity without additional references. And we do have a presentation that we had last year in our Women Who Code Philadelphia group that we have recorded on time and space complexity. we went over that. So the sort of last thing that you want to talk about is how you would break it. Things like what could possibly go wrong? What could a user or caller do that would completely mess this up? And this isn't about breaking your code. It's about thinking about how your input could be different, how to make your code robust. So for example, find min or get min on an empty queue. What's that going to return? Now, if you looked at my code implementation, it would return -1 because everything was initialized to -1. And maybe that's okay, maybe it's not, but you do need to know that behavior, this weird case where why would somebody call get min on an empty queue? Things like, what if somebody put in a number? Now, whenever you get integer questions, this is always great. Well, for Java developers anyway, what if you put in an integer that's bigger than max int? So your number is too big to be stored as a number. That's always a good one. So things that are like, who would do that? Why is that number so big? That kind of thing. And as an aside, I say Java because Java has two numeric types that are not floating point, integer and long. And so this becomes an interesting interview question for that language. Okay, other tips related to this. Check in with the interviewer. And I've mentioned this a couple of times. You want to check in with them. And I know it might seem a little odd. Is this what you want me to implement? Is this the solution you're looking for? Do you want me to focus on insert or remove? Because they need to evaluate you and you want to give them the best data possible. Be careful not to spend too much time with clarifying questions and examples before coding, maybe 5, max 10 minutes on this segment. Sometimes you just have to take a leap and start writing the code because that's another piece of data they need. It can be a little tricky to find the right balance, but with practice, it gets a little easier. And it's okay if you can't get to time complexity and test cases. Some interviews, they kind of want to see you rearrange your code and refactor it, and they'll give you a curveball and say, I changed my mind, please make this generic, not specific to integers, and you don't get to time complexity and test cases. They might be evaluating something else. So how do you practice this? You know, we know how to practice the code, we start writing code, but what about all these other things? Practice all the steps. I realize this bullet, thank you for reiterating what you just said, but I mean, when you look at an interview question on your interview practice sites, before you start coding, start writing out or talking to your cat about how you would answer the interviewer in this question. Repeat the question, come up with examples yourself, all before you start coding. Write and review your code without running it. What we tend to do is we write a bit of code and we run it. We say, oh, I forgot a semicolon. And then you add the semicolon, you run it. Oh, I index out of bounds or wrong type. And we just keep running it and wait for the compiler or the runtime to tell us, hey, you did something wrong. That's not going to work in an interview. When you write your code practicing it, don't run it. Try to walk through your code and find your own bugs. You may not be in an interview where you can run your code. So this is the summary. Now you might be able to rearrange the steps that work for you, combine them, split them out, whatever works. But the idea is you spend some time clarifying and then you describe what you're going to do, you code, and you analyze it. Hopefully you have an easier time communicating with your interviewers, making your interviewer work hard trying to figure out what you're thinking is not going to go well. Try to save them the work and show them what a great engineer you are by telling them all of this stuff up front. Okay, so any questions on that or Heaps or anything about interviews at this point?
Yeah, I did have a question about the Heaps actually. I guess it was kind of unintuitive to me that you would use the last number in the heap. Like, why wouldn't you use like something from the second row? Do you have less sorting to do?
Yeah, the reason why you use the last one, it's easier to maintain the size. Now, the implementation I chose uses the last one, but you can, there's many variations of how to implement a heap. This is just the simplest one, where you choose the last element in your underlying array to make it easier to manage the size of it. So you're only doing so many swaps. Whereas if you pick an internal node, you're going to have to manage more swaps across different paths. So that's right, the complexity is a little simpler.
Gotcha. Thanks.
I don't have a question, but more of like a comment about the second part of your presentation, because I just did a mock interview, I think 2 weeks ago. And if any of you know me, I'm really good at talking. And so I was like talking through everything I was doing while I was coding out the problem. And one of the benefits that I know you mentioned is like the interviewer can know where you're going with the problem. And I was like circling around the answer that I wanted, and he was like, maybe you should try this method, kind of like nudging me in that direction. Whereas if I wasn't vocalizing my thoughts, you would have been like, what's this girl doing? Like, she's just scratching her head and looking at the computer, you know? So I think what you said was really good advice, and it's worked for me.
The feedback I've gotten from interviewers is, I have no questions to ask you because you answered them already. So it's usually a good sign when you've covered all of your bases. Though there's always a balance. Spending too much time in one part can always negatively impact the other, but the problem I see and the problem recruiters tell me about the most is we couldn't evaluate you because you didn't finish your code and you didn't say anything. So thank you for sharing that. Proof of communication being really important in interviews, Meg.
And that's one other thing, like I was thinking of the space-time complexity, and I was like, I know there's a smarter way to implement this solution, but I also know I only have 15 minutes left. So I'm going to just get this code done and go back and refactor if I have time. And I ended up not having time, but I said that out loud to them and just kept plowing through the problem. So like they understood that I knew about space-time complexity and big O notation and what those concepts were. And some of the feedback was, a lot of times I'm having to give that lesson as part of the feedback. So that's really good that you know that, just like learn it better. So again, communication.
Becca, did you want to help wrap up?
Yeah, thank you, Alicia, for giving this talk tonight. This is really helpful. Let's stop the recording.